All right, let's get started. So on Tuesday, we talked about Logit, and today we're just going to do, again, a Python exercise to apply Logit to the data set. So the example is what we started um, at the beginning of the slides on Tuesday. So there is, okay, so let me share my screen. So all of the files are in the Google Drive folder. So you can see in the folder lecture 3, there is the CSV file, which is our data. And then the Python codes. And then there's also a Word document that describes what this data is. Okay, so this data is from Federal Reserve Bank of Boston. And it has the mortgage applications of about 2,000 people. And so each observation here is a person. And for each person, you see a number of information about that person, including their income and the debt they borrow. So you have the full list of the information here. So for example, first of all, you have the type of the loan and the amount of the loan. And then you have the characteristics of the property. And then the information about the applicant, what their race is, what their gender is, and whether they're married, whether they're self-employed, how many years they're employed, etc. Okay, so all of this is valuable information to the mortgage lender to assess how credible the borrowers are, right? And our goal here is to test whether whether race is a significant predictor of the approval decision, because by law it should not be, but this is the data and we're actually going to test whether that is a significant factor. So we'll come back to this document later, but let's first open. So every time for the examples, you should just copy the file I have, like right click on this Python notebook and then make a copy. And then have that copy in your Google Drive, and then you can make edits on it, okay? All right. So first, the usual stuff, we import a bunch of libraries that we're going to use, like NumPy, Pandas, and then the function for Logit and Probit, like these classification models. So there are actually two ways to do it. The first is using the stats models. So remember, that's the one we actually used for regression in the first lecture. And the second way is to use the scikit-learn, which I think you have already seen for the machine learning part of the like 650. So I'm going to show you that they actually will produce the same result. So it's just two different ways to run Logit. Okay, so let's import these first. And then we load in the data. So the data is a CSV file. And for these variables, they don't actually have the variable names. It's all a bunch of codes. So you have to sort of go back to this document and see what each of these variables mean. For example, S5 here is occupancy, and then it tells you what each of these values mean. So one means owner occupied, and that's the most common type. And then 2 is not owner occupied, and 3 is not applicable. And S6 is the loan amount. So you have like 88, 118. I think this is in terms of thousands. Okay, so this is our data. So the first thing we do is to make several sample restrictions, and we just focus on that subsample for now. So the first restriction we make is we only look at male applicants so that we don't bring in the additional gender consideration. And also when you have both males and females, you have to consider their families, so it's like more complicated. So the way you do that is to locate the index of the observations where you have the gender is male, okay? And the gender variable is S15. Again, it's in this document, so you can search sex, and then S15, if it equals to 1, it means that it's a male. Okay. So that's the first restriction we make. And the second one is we drop the self-employed people. It's actually a very small fraction. And then that's the S27A variable. So we want that variable to be equal to 0, so that it's not self-employed. And then the third criteria is that we drop if the private mortgage insurance is denied, because if that's the case, then the mortgage will be denied. So then it's not a very interesting case, and it's about the decision made by the insurer, not the mortgage officer. So that's the S53. We want that to be 0. And finally, we want that there's no public recorded default at the time of the application. Again, that's a very few cases, but if that's the case, then I think it will be automatically rejected. Okay, so that's
Professor.
After we make those restrictions, so you can see that let's see how many observations we have. Okay, so I think we end up with like 1,484 observations. So it's close to 1,500 observations. Okay. And then we create some of the variables that we're going to use. Okay, so first we create a dummy variable for race. So if the applicant is African American, and then we create the variable black equals to 1. So the way we do that, again, it's first you locate the index of the observations where the race variable equals to that particular category. Okay, so that's this variable. So if it equals to 3, then it's black. And then for those observations, the value of this variable is 1. Otherwise, it's equal to 0. So it's like an indicator variable for whether the applicant is a minority. And then you can see the distribution of that variable. So it will only take 2 values, 0 and 1. And then the mean is 0.09, which means that about 10% of these applicants are Black. Okay. And then we create also our outcome variable. So outcome variable is whether the mortgage is denied or approved. So here we create a variable called denial, and that equals to 1 if it's denied, and if equals to 0 if it's approved. Okay, so that's the S7 here. So equals if that variable equals to 3, it means that it's denied. Okay, so that's those are the observations where we want to assign the value to 1, and then we assign the rest of the observations to 0. And you can also describe that variable. So the mean is 0.07, which means 7% of the people are denied, okay? And again, this is a 0, 1 variable. And this is our outcome variable. So when our outcome variable is a category, so these are 2 categories, right? Denied, approved. And when it's a category, we should use Logit or Probit, which are the classification models. But before that, let's just try that for the OLS. Okay. And even before that, we can actually calculate the denial rates for the subsample of the Black applicants and the non-Black applicants. So the way you do that is to restrict to this subsample, right, where you have Black variable equals to 0, and look at the denial variable and look at its mean. So that's the non-Black population. There are 1,300 people, and the denial rate is 0.06, okay? And then we could also do that for the Black population. And then you get a mean of 20%. So that's much higher, okay? So compared to 6%, okay? So if you only look at these summary statistics, then you might conclude that this is a significant factor, and they're somewhat biased in their decisions, okay? And this is a very big bias. And if you run the OLS regression with just this one variable, so this is a bivariate regression, right? And if you do that, we will get the coefficient is 14%, right? Which is just equal to the difference in the denial rates of these two populations. So this 20% minus the 6% is about 14%. And that's because when you're doing an OLS regression, you're basically just comparing the averages of these two populations.
Professor, can I ask a
Okay.
question?
So next, let's be a little bit more sophisticated and add some control variables. So why do we want to add control variables? That's because the difference itself does not say that this is a significant factor, right? It could just be reflecting something else, like differences in income and education and so on. So we want to add several control variables. The first one is the loan to value ratio, which is the amount of the loan divided by the amount of the housing price. So you can find all of this in this document, right? S6 is the loan amount, and S50 here is the appraised value of the house. Okay, so let's just try to construct these other few variables. So let me just go over what they are. The first one is whether they're single. The second is whether they go to high school. And third one is whether they live in a condo or a house, okay? And there are a few others, but and then next, let's just run an OLS regression with all of these additional control variables and see if the coefficient changes. Okay, so I'm giving you just 5 minutes. So you can just work on your own. I'm not putting you into breakout rooms for now. And if you have any question, you can just type in the chat. So Jack, you have a question?
Yeah, can you share your screen again and go
I see
back?
you raised your hand.
Can you hear me? Can you hear me?
Oh, sorry, I think my volume is muted. Okay, sorry, I didn't hear you.
Can you hear me now? Hello?
Yes. Yep.
Can you share your screen again? Back to
Oh,
where you just were?
sure.
And can you scroll up, please? So when you print out these describe the two tables, can you talk about what they're doing exactly again when black equals 0 and black equals 1?
Okay, so this is calculating what is the average denial rate for the Black applicants.
Okay.
And sorry, this is the non-Black applicants, and this is the Black applicants. So we want to see what is the denial rate for these two population and how they compare.
And so for non-black, it's 6%, and for black, it's 20%.
Right.
Okay. Thank you. That's what I was wondering.
Mhm.
Thank you.
So high school is, yeah, if you have more than 12 years of education, including 12.
We can't hear you.
Oh, sorry. Can you hear me now?
Yes.
Okay, sorry. Okay, so now let me go back. So we the first variable we create is whether it's single. So we look for that variable. So it's this S23A here. And if the value of that variable equals to U, and then for those observations, the value equals to 1 and otherwise equals to 0. So that creates a dummy variable indicating whether the applicant is single. And then for high school, it's the school variable, tells you the name of the, so here, tells you the years of education. And if that variable is greater or equal to 12, okay, and then the value of that dummy variable equals to 1 and otherwise equals to 0. And finally, we look for the condo variable, which is S51. So if that equals to 1, if it's a condo, and that condo dummy equals to 1, otherwise equals to 0. Okay, so this creates 3 dummy variables, but it's all in the same way as we've done above, right? You first find the index where it's in that category, and then if it's in the category, it equals to 1, otherwise you fill the rest of the missing ones with 0. Okay, so now we have all of these variables. Let me keep this part on the screen. So now we have all of these variables, and we run a regression, just revise the formula to add all the additional variables. Okay, so we have the debt to income ratio as 46, housing expense to income ratio as 45, and loan to value ratio, which we just created, and credit history. So that's S43 and S42. And then the single dummy, which we created, high school, which we created, unemployment rate, which is the URIA, and then the condo dummy we also created. Okay, so we add 1, 2, 3, 4, 5, 6, 7, 8, 9 variables. Okay, so now the regression has 10 variables in total. And if we run that regression, oh, yeah. And that gives you a coefficient of 1. The one we're interested in is the black variable, right? And that coefficient is 9%. What does that mean? It means that, go ahead.
It just means that on average, controlling for the other variables in the regression, a loan applicant is about 9.3% more likely to be denied.
Exactly. Is that smaller than before or bigger?
Smaller.
Smaller, right? Before we had something like 14%, and now it's 9%, so it's definitely smaller. And when adding all of these controls, they sort of absorb the effect of the black a little bit, but still we see a 9% difference. And you can do a t-test, right? And the t-statistic is 4. The p-value is 0.000. So it's still a very statistically significant effect. Okay, so you can reject that that effect is 0. Okay, so that's the regression with controls. But as we said on Tuesday, you cannot just run OLS regression, right? Because this is a nonlinear model. So the right way to do that would be a logit model. Okay, so the way to do logit is actually quite simple. Right, if you compare this code and this code, it's basically the same, right? The only difference is that you're replacing the OLS here with the logit. And that's because this is also using stats models, so they kind of have the same language. And that tells the computer to use the logit to fit this equation with the denial being the dependent variable. And then you have these 10 explanatory variables. And then you can print out the result. Okay. So now, if you look at the coefficient, it is 0.82. Okay. And what does that mean?
That's the odds ratio.
That's the odds ratio, exactly. Okay, so you can use the odds ratio to interpret it, but it does not mean that the denial rate is 80% higher, right? That would be absurd. But if you interpret it using odds ratio, you would say a 1 being black increases the log of odds. Increases the odds ratio by how much? 80%. Okay, so that's 100 times beta. So that's one interpretation. So it's still a positive effect. And if you want to see how that translates into the differences in denial rates, right? So denial rates is just the probability of denial, right? If you want to translate that into differences in probability, you will need to do the marginal effects. And here, there's a way to just calculate the marginal effects after you estimate that equation. Okay, so you can use the results and then this function called get marginal effects. And there are several arguments. The first argument is at which point you calculate the marginal effect, because we have discussed the marginal effect depends not only on beta, but also on the value of x, right? Because it's the derivative and it's a function of x. So that if it equals to mean, that's to say we want to evaluate the marginal effect at the average x. And then the method is just to take the derivative and then I think this argument is the variable that you want to calculate the marginal effect. Okay, here we don't care about all the other variables. We only care about the black variable. And then the last one, dummy. I'm not sure what that is. Okay, I don't think that's very important. And then this will print out the marginal effect. And you can see that this is more in line with what we see earlier, right? And the coefficient here means that the denial rate is about 5% higher if you have all the other variables at the average value. Okay. So you can already see here that logit gives you very different conclusions, right, from the linear regression. Linear regression, if you do without controls, it's 14%. If you do with controls, it's 9%. And with logit, the marginal effect is about 5%. So it, again, gets much smaller. And if you do the linear regression, you would conclude that there's a huge bias, but now the bias, it's still there, but it's actually smaller. And then, of course, usually we do logit because we want to predict the probability. And then you can also use this predict function to give you the prediction for every observation, okay, given all of their x's, what is the probability of denial? And basically the way you do that is to just specify what are the variables that you have to predict. And then results is the results that we just estimated, and then use that model to predict. And this creates a new variable, sort of, which is the predicted probability of denial. And you can summarize that variable. And you can see that the mean is 7%, which is exactly the same, okay, as the mean of the actual denial. But it is not 0 or 1 now, right? The actual denial is only takes two values, 0 and 1. But now it's actually going to be something between 0 and 1. It will never be 0 or 1. Because it's kind of like a CDF, and only when it goes to negative infinity or positive infinity, it will be equal to 0 or 1. Okay, so the minimum is very close to 0, but not 0. And the maximum is like 87%. Okay. And you can even do that prediction for different subsample. And that will, again, actually give you the same average. Okay, so for the non-black sample, the average is, again, 6%. The black sample is 20%. And then another way to estimate the logit model is using the scikit-learn. Okay, so from there, you import this function called logistic regression. And well, the first is just some specifications of how you would estimate that. And then the input is what are the exogenous variable. Again, these are the predictor variables in our data. And then the second argument is the variable that's to be predicted. And that will also give you the coefficient of each of these predictor variables. And black is the first variable, so that coefficient is 0.82. Okay, so it's very similar, basically the same as what we had here. So here it's 0.8214. From scikit-learn is 0.8230. It's a little bit different because here you're also doing some regularization, but that only that's only very minor difference. And then you can also use that to predict, and you can use that to plot the ROC curve that we talked about. And that will give you an assessment of how good this model is in terms of predicting the probability.
So, sorry, in terms of the prediction, do we need to separate the data into a chunk of data for us to do the prediction?
Are you thinking about like a training sample and test sample?
Yeah, I don't get these sort of, yeah.
Okay. Well, you could do that too, right? So you could fit the model using the training sample. I think
Yeah, so how do
think
we,
that's what you're gonna do in the problem set. So you have like a training
but-
sample.
right, but how do you do here for the prediction? I don't get the,
Oh, so okay, let's go back here.
sorry.
So the line that you do the prediction is here, right? This line.
Yes,
And the input is the exogenous variables.
okay, so
right?
you create another chunk of variable in order to test, to test the model, right? The model is based on our original data.
Okay, so let me try to explain. So you can put anything here. So this part that I'm highlighting here, you can put anything. It doesn't have to be the data itself. It can be any value of the X. Okay, and then
Yeah.
that will give you a prediction.
Okay, I got it.
So, yeah, for example, you can estimate the model using a training set, and then so you can have like train. Sorry, that is anyway, you get the idea, right? So you estimate the model using the training set, and then you can use the test sets like predictor variables to get the prediction in the test set.
Yeah, I got it. Yeah.
Okay. Yeah, so
I also have one more question here. So when you're doing the after the predicting, why the result we got is the decimal? It's not 0 and 1 because 0 and 1 is what we want, right?
sorry, I can't hear you very clearly. Could you say again?
So yeah, so when we are doing the predicting here, so after the predicting, we got a result. It's all from 0 to 1 decimal, and it's not 0 or 1. But
Yes.
the reason we are doing the logis regression is that we are trying to get a result, whether it's delay or no, right? So I think the result we get here should be 0 or 1 after we like doing the prediction.
No, the prediction is you can think of it as a probability. So that's like the probability of rejecting or approving. It won't be 0 or 1. And to get 0 or 1, then you can add a threshold. But
so how we decide the threshold here, if we want to do that, or just by our own objective?
Well, it depends on what you want the logit model to do here.
Yeah. But we are trying to predict whether the loan is going to delay or no. So we already done this data predicting. So, but as a result, we just got the percentage of the probability the loan is going to default. But we still kind of cannot figure out whether the loan is going to default after we getting a new data here.
Right. So, well, then you can sort of decide the threshold, right? You can, if the threshold is very low, then everyone gets accepted. If it's very high, then everyone gets rejected. And then you can sort of vary the, you can just choose whatever acceptance rate you want.
Okay.
And
Thank you.
then, yeah, so I think you're sort of thinking about a question where it's kind of like you're predicting default, right? And then you want to allocate the limited amount of funding to people who are least likely to default.
Mhm.
I don't know if you're thinking about that type of situation. So in this particular example, we're just using Logit to sort of like test what is the effect of the black variable. Okay, so this is one use of it. And then yeah, so here Logit is more like trying to predict how they actually make the decision.
So it's more for interpret instead of the prediction here we are doing.
I mean, for your question, you can always easily just set how many people do I want to reject, how many people do I want to accept, right? And then you can just accept the people with the highest with the lowest predicted probability.
Okay.
But this model, its prediction will not give you 0 or 1. It's more sort of like a rank of whether they're more likely to be rejected or denied, rejected or accepted.
Yes, thank you.
Yeah, and then the RC curve is sort of, you can vary the threshold and see how good the X's are in terms of predicting the classification.
In this case, since we're not splitting, since we're using the whole sample, our prediction is the sample mean, right?
No, your prediction is the probability. That's all.
Is it the sample mean probability,
No,
or is it? Okay.
What do you mean the sample mean?
Like, is our prediction from this the same as if we were to is it the same as the mean denial probability in the sample?
Well, the mean of the predicted probability is the same as the mean of the actual denial.
Okay,
So you
thank
can
you.
see here, right? So this is a predicted probability. The mean is 7% and the actual mean is 7%. Well, so I think this, again, going back to my previous, to the previous question. So this is kind of specific to Logit, because here you only have 2 categories. So then the prediction is, it will give you is the probability of you ending up in one category versus another. But actually, as you'll see later, when you are doing the multinomial Logit, when you have the multiple categories, the prediction it gives you is actually the category. Okay. Now let me take a little break from here, from the coding, and talk about how do we estimate the standard errors, okay? Because when you estimate these models, they actually give you standard errors, but it's not very correct, actually. So the best way to do that would be to bootstrap. And then I don't think Python has a function to do that. So you sort of have to write your own code. And that's what this whole big chunk of the code is about. But let's first go back a little bit and let me explain what Bootstrap is. So did Professor Kozak talk about Bootstrap in the previous courses or no?
Yes, he
Yes.
did.
Oh, he did. Okay. So can anyone just briefly explain to me what is Bootstrap?
So you would take your sample and for each iteration, you would take a subsample and you would compute the parameter that satisfies your objective based on that subsample. And you would take a large number of subsamples and average the parameter across all iterations.
Yeah, that's pretty much it. Okay, so actually have some slides on it too. So if you don't remember, you can go back to my slides and take another look. But basically, it's just you are treating the sample you have as the true value, and then you are redrawing the sample. Okay. And you're drawing the sample with replacement. So it's kind of mimicking the data generation process that the data generation process is drawing sample from the actual distribution, but you are drawing sample from the sample distribution. And then you draw it with replacement and do that many times. And each time it will give you a new sample. So that's a bootstrapped sample. And then from that sample, you can estimate the beta, the parameters. And then for each time you draw a sample, you get a different beta. And you do that many times, like 50 times, 100 times. And then you get many betas, right? 50 betas, let's say. And then you look at what is the distribution of that 50 betas. And the standard deviation of those 50 betas would be your estimate of the standard deviation of the estimated beta. And then you can also build on top of that what is the confidence interval, and you can do hypothesis testing. So that's the idea of the bootstrap, and it can apply to anything as long as the distribution is sort of continuous. So there's no when you perturb the data generating process a little bit, as long as the sample distribution doesn't change a lot, and then bootstrap would work. So it doesn't require your beta to have any specific kind of distribution. So that is a very flexible way to estimate the standard errors and the distributions of your estimates. Because for a lot of the estimates, you don't have something as clean as the linear regression where it's just like a t-statistic. Okay, what is the question?
Professor, can you explain that the standard deviation of the beta is, I don't know what's the standard deviation of the beta is, like, what is the meaning of that?
Because the beta you estimate is also a random variable, right?
Right. So
Because all of your x and y's are random variables, and the beta is a function of the x and y's, so it's also a random variable. And then if it's a random variable, it will have a distribution. So basically that's because the data you observe is kind of like one realization of the reality. So you can think of like there are many parallel universes. So we only see one universe. But there are actually many parallel universes, and in each universe you have a different beta. So the beta kind of has a distribution. Does that make sense?
the standard deviation of the beta is like the probability is,
No, like in
because I don't know what's the meaning of that.
when you're
How
doing
do you calculate
Okay.
I know how you calculate that, but I just don't know like um, what's the meaning, like
Like
what's the meaning of
conceptually.
this? Right.
Yeah, so it's just what I said, that beta is a random variable. So it have a distribution just like any random variable. And
Okay.
then that will have a standard deviation. Okay.
Okay.
So like the data that it's generated, there is some noise, right? And those noise are all random. And given another realization, another set of noise, you would have a different beta.
Right.
And if that noise is big, then your beta will have a big standard deviation.
Okay, cool.
So Professor, if our sample size is big enough, right? For instance, is it necessary for us to do the bootstrap here? We do bootstrap. One of the reasons is that, I suppose, is that because the data we can get is limited, right?
It does not actually matter what the sample size is. The reason we do bootstrap is that this is a complicated estimator because it's the maximum likelihood, right? And for the linear regression, if we assume the errors are normal, and then the beta will be will have a t distribution with a finite sample. So that's a distribution that we know, but with this complicated estimator, we don't know what beta's distribution is. Okay, so that's why we do bootstrap, because we don't know what the distribution is.
Okay, thanks.
Okay, but all of this will in the end just be used for testing some hypothesis. That's it. Like in the linear regression, you would calculate, so the beta will have a t distribution, right? And you can sort of see what is the t statistic. So if beta is very far from 0, and then if its standard deviation is sort of small, and then you can reject that the beta is not equal to, you can reject that beta is equal to 0. So all of this in the end will be just used for hypothesis testing and sort of see what is the confidence interval of beta.
Yeah, thank you.
Yeah, because like here we estimate that the marginal effect like is 5%, and that could be a very precise estimate that we're very sure that the effect is just 5%, or it may be a very noisy estimate that it can range anything from minus 10% to plus 20%. Okay, so then that sort of matters, like how confident are you in the estimate you get. Okay. Well, so let me just share this. Okay, so so basically you can look through this. I'm not going to talk about it in too much detail, but this is the function where you do bootstrap. Basically, you just draw from the sample with replacement, okay, and get a new sample, and then do estimation on that new sample, and then calculate the standard errors of those betas, and then also get the confidence interval and so on. And once these are just functions that you define in Python. And then we have our equation, which is the same as before. We can just apply this function, okay? Call it whatever name. So logit wrap, actually, we define it here to sort of fit the logit model to the data. And 50 is the number of times you draw a sample. Okay, so it's the number of betas you get. Equation is this equation here, and the data is our data. So that could take like 2 seconds to estimate beta for all of these 50 iterations. And then it will give you the estimates and their bootstrapped standard errors. Okay, so the estimate will just be same as before because bootstrap only matters for the standard error. And the standard error here is 0.28. So if we compare with before, so this is 0.285. Before it's 0.264. So it's sort of getting a little bit bigger, but not that much, only a little bigger. Okay, so then the p-value is no longer 0.000, but 0.004, but still it's pretty low, so that we can still confidently reject that black has a zero effect. Okay, so that's sort of it. And the next part is for you to do some exercise. So we've already done it for Logit. And what I wanted you to do is to do it for Probit. You can first try that with just the plain vanilla without bootstrapping. So the way to do it is just use the Probit function. Okay. So there's also a thing called Probit. So you just replace the Logit with Probit. And then also try to do that with the bootstrap standard errors and calculate the marginal effect and see if that's similar or different from Logit. And then the next thing is I want you to try the multinomial Logit. So I already wrote the codes for you. The only thing you need to do is to find something in the list of variables that you can estimate using multinomial Logit, because only specific kind of dependent variables, right, where you have several categories and they're not ranked, that you can, you should estimate with multinomial Logit. So you should find a variable like that and then just plug that in here and estimate that. And finally, order Logit, same thing. You find some variable that has several categories, but it's ranked from highest to lowest, and then plug that variable here, and also specify what variables you want to predict that. So it can be anything. Just try it out to see what the results and the predictions look like. Okay. So I'm gonna give you like 15 minutes and we'll come back and finish those. Okay, so I'm gonna open 11 breakout rooms, or maybe 12. And then I will try to go into every room to see how you're doing, but I may not have time to go into all of the rooms. And you can also raise your hand if you have a question. Okay. So Angha and Poojan, could you join your rooms? Okay, Jack and Alexander. So are you back because you have a question?
I'm back because my breakout room, the other two people weren't talking or doing anything.
Okay.
So I just came back here to wait.
Okay, then you can just work on your own. Or I can put you and Alexander in the same room.
I'm just working on it by myself.
Okay.
Yeah, basically same vibe. The other guy just like dipped.
Okay, you can just work here and while the TA Kai is here, so he can also answer your questions while I'm in the other rooms.
Okay. Professor, could you put me in a group so that I could see what other people are doing as well?
Sure.
Can you change my breakout room? Nobody's picking up.
Okay, let me do that. So I'm gonna put you both in the room 7. Okay, find you.
Are we done with class today or?
All right. So did anyone get what is the marginal effect from Probit? Am I muted? No.
Point 0.02625.
0.02, 0.02,
No,
0.06, 0.0625. Yeah. Okay. Anyone else? Do you all get the same number?
Yes, same number.
Okay, let's see. I think that's also what I get. All right. So basically, you don't have to rerun that whole part about the bootstrap with models because so this part it's the same for Logit and Probit. You just need to change this part, okay, and replace it with replace the Logit with Probit, and then when you run that and print out the results, this will be the coefficients and bootstrap standard errors from Probit. And the coefficient looks very different, right? It's like 0.43. Before for Logit, it's 0.82. So the coefficient looks pretty different. This is also very significant with the p-value under 1%. But then if you look at the marginal effect, so some of you get the same number as mine, which is 6%. And if you look at Logit, I believe so that's 5%. So these two are actually very close. Okay. So again, that's the reason why to sort of interpret how big this effect are, you always need to calculate the marginal effect. If you only look at the coefficient, it's very hard to know. Like for Logit, you still have the odds ratio interpretation, but for Probit, this number itself doesn't mean anything, okay? So you have to take the derivative and multiply that by sort of the PDF to get the marginal effect. And then you get a very similar number as Logit. And that also sort of illustrates, usually Logit versus Probit produces very similar results. So the distribution that you choose does not matter as much, but both of them are still quite different from the OLS. So in OLS, we get, I think, 9% with controls, right? So which is much bigger. But here, these two are within, they're within 10, 20% of each other. Okay. And then for multinomial Logit, so I'm leaving a blank here. What for the y, for you to choose what is the y variable, because not every y variable is suitable for multinomial Logit. For this, we want something that has several categories and it's not ranked in particular order. So which one did you pick?
We did the number of family units, S20.
You did the S20. Okay, so let's see for S20, what are the values? Okay, I don't know what happened there. It's like, I'm sure that's a error, right? Do you see the same thing, that there's some huge numbers?
Yeah.
Okay, interesting. But that doesn't matter, I guess, because these, we are just treating them as 4 categories, right? We are not regressing the numbers. So this is okay. So let's try that. And you also get, do you also get something looks like this?
Yes.
So this would be the result you see from multinomial Logit. So here you have 4 categories, and that would print out 3 tables, okay? And that's because you have a different beta coefficient for each category, and you are normalizing only one of them to be 0. So for Logit, 2 categories, so you only have 1 table. So here you have 4, so you have 4 minus 1, which is 3 tables. And this is, so the category that's kind of omitted here is equals to 1, okay? And then equals to 2 has these coefficients, equals to 3 has these coefficients, equals to 4 has these coefficients. So if you only look at the coefficients, I guess, so what does 2 mean?
2 is 2 family units.
2 family
think.
units. Okay, so I guess black is more likely to be in 2 family units. But that's really a very small number, right? There are only 10 of them, and there are only 2 of the other categories. So it's hard to say how precise these effects are.
I think when you get into the multiple, like 3 and 4, one thing I noticed was I think education starts to get significant, or high
Okay.
school.
Okay. I think, did anyone try anything different? I think what I tried before was the S7. What is the S7? I see. So S7 is sort of like whether it's accepted, rejected, or withdrawn. So there's 3 equals to if the mortgage is withdrawn. So it's actually the same variable as our dependent variable before, but it has 1 more category. And if we try that, we can see that compared to the 1 category, which is accepted, black has a minus coefficient here, so they're less likely to be withdrawn, right? They're less likely to be approved and not accepted, and they're more likely to be rejected. Okay. So those signs also have meanings here. But again, if you want to know the marginal effect, you have to sort of also do the marginal effect calculation, and also you can do prediction. It's just the same thing as before, because this is all in the same kind of library. Okay, now finally, let's try ordered logit. So this is for some variable that has several categories, but it's ranked. Okay, so there's sort of highest and lowest. So what is the example you chose?
We did credit history, S42.
S42. Okay, so there's 1, 2, 3, 4. What do they mean?
It means most people pay their mortgage, and then the next most popular group is people that don't have one at all. So it just says people don't default.
Right,
Usually.
that's great. So 1 is no late payments. 2 is, it's a little bit complicated, right? 2 is like no payment history. You can say that's like a little worse than no late payments and a little better than having some late payments. And 3 is 1 or 2 late payments, and 4 is more than 2 late payments. Or you can use S43, which is also sort of ranked, okay? So let's try S42 here. So here you have to install another library, unfortunately, for the ordered logit. And then we have to sort of redefine the exogenous variable, because before we have S42 in the exogenous variable. So we don't want to have the same thing in X and Y variable. So we drop that one. And then put the S42 here. And do that. Okay. So that gives you these coefficients. Okay. So black is the first one. So it has a positive coefficient, which means black is more likely to be in the bigger category. Well, bigger category is the one with more late payments, right? And so that's sort of the meaning of the sign there. And then you can also do prediction. So I'll just write it here. So if you want to predict from that, let's call it S42 predict, or S42P equals to okay, so it looks very similar as before. And then we can summarize that. Not describe. So the prediction here would be 1, 2, 3, 4. Okay. What? Oh, sorry. Okay, but it's kind of interesting here. It only predicts 1 and 2. Okay, so here the distribution of the predicted category doesn't have to be the same as the distribution of the actual values. And that's because there is very few 3 and 4s in general, so that when you fit the ordered logit or ordered probit model to it, and then it will just not assign any observation to those categories. So that could happen, okay? Or you could try other stuff, like the example I did before was S43. So there you have these 6 categories, and it's also ranked from the best to the worst in terms of the credit history. And you can sort of use the other stuff to predict it. And again, black sort of have a positive coefficient. And then if you look at that prediction, okay, sorry, call it S43. And then you can see that you have the 1, 2, 3, 4, 5 all in here, but you're missing the 6, okay? So it's a little bit different from logit. So logit always predicts a probability, but if you do this ordered logit, or if you do the multinomial logit, it will actually predict the category. But the distribution across these categories will not necessarily be the same as the actual distribution. And these are your predictions. And you can also sort of do that, fit the model to the training set and then predict for the test set. Okay. So that's all for today. And now you should be able to do all of the problem set, and we will also assign you to a group before the next lecture so that you can start working on the group project. Any questions?
Yes, Professor. So can you share your screen again?
Sure.
Thank you. So I'm just asking the co-ifs you get from the ordered binomial. So like there's 6 categories, but there's only like which category is those co-ifs stand for?
Oh, you mean this coefficients?
Yeah.
That's a great question. So here, because it is ranked, okay, so that this when the coefficients are positive, it just means that you're more likely to be in those higher ranked categories. But before, for multinomial logit, those are not ranked. So you would need to have one coefficient for each category, which says you're more likely to be in that category than in the other categories. But here, when it's ranked from the highest to lowest, then when it's positive, it just means that you're more likely to be in the higher categories.
But you do know like which category, because there's like higher, there's the first higher and second higher, you don't know, right?
No, that's your prediction, right? So it's your prediction right here. Depends on how high you are. It will give you a prediction of 1 or 2 or 3 or 4 or 5. And if you remember from the lecture, right, the things we're estimating here is both these parameters and also the thresholds. Okay. So then when you have the parameters and the thresholds, then you can assign each observation to one of the categories.
And the total number of the value count should be equal to the total number in column 43, right?
Of course. Yeah, this is the same, have the same dimensions. So you mean the numbers summing up here is equal to the number summing up here?
Yeah.
Sure.
Thank you.
Okay. All right. Thank you, and I'll see you next week.
Professor, if you wanted to set up like an office hour, do we just email you?
Yeah, if
Mhm.
you can make the Tuesday night office hour, that would be the best. But if that doesn't work for you, you can also email me.
Okay, thank you.
Mhm.
Oh, and I'm sorry, I just wanted to ask, for the final exam, would you be providing us with like a review session and also
Yeah. There will be a review session in the last week.
and would you let us know like what to focus on when we're studying and everything?
Yeah.
Okay, thank you.
And I will give you some sample questions, I guess.
Okay, perfect. Thank you.
Professor, can I ask the problem set question I asked in the breakout room?
Yeah. Okay.
It's from.
So let me wait a second. Let me open the problem set first.
Okay, it's from the housing prices section.
And
it's the question 3.
Question 3. Oh, okay. Yeah, so it's not in Stata, sorry. Run an F-test.
Just run an F-test, is that what you're saying?
Yes.
Okay.
It's a typo.
Okay, thank you.
So what will be the structure of the final exam? Is it going to be like the problem set or a different structure?
It will be very similar to the problem set, but it will be definitely shorter and yeah, but it will be in a similar format.
So we are going to be programming during the final.
Yes.
Okay, thank you.
And also like some some conceptual questions too. So just like the problem set, you will see.
All right, thank you.